I will present our result with Bruno Loff about lower bounds for dynamic data structures. So, dynamic data structures, we want to maintain some encoding of data in memory, and we somehow want an algorithm, efficient algorithm for updates the data in the memory, and after the updates, we want to do some queries which which gives us some information about the data. And a long-standing open problem in this area is to prove some unconditional polynomial lower bound of a trade-off between the update time and the query time. So now I will present some concrete dynamic data structure problem, which is called multiphase problem, and it was introduced by Patrascu in 2010. So we have some data x1 to xk, which each xi is 0, 1 string of length n, and we wish to store them somehow in the memory. So we want to store some table and of cells, and each cell have w bits, and we have s cells, and this should be somehow efficiently computed in time tp. And the standard setting is that the k is polynomial in n, and s is polynomial in k, and w is logarithmic in n. And after the first phase, when we store the original data, we do some update. So we get another string of length n, and we somehow want to store it in the table. And how we do it is by update decision tree. So we have tree, and each node of the tree read some cell from the table, and also can write to the cell. And according to the value of the cell, it can decide to go to another node of the tree, and then in the other node, we decide to read another cell, and so on. So we have this tree, and the depth of the tree is our update time. And after the update, we have a query, which the query is one index, and for that query, we have also a decision tree, but now we only read the cells. So we read cell C, and again, according to value of the cell C, we read another cell, and so on. And in the leaf, when we arrive to some leaf of the tree, we should output if the string xi, which we are given at the beginning, and the string y, which was the update string, is if these two strings are disjoint or not. It means if there is some index j, such that the jth bit of xi and jth bit of y is both 1 or not. So you can interpret this function if you interpret those strings as characteristic vector, as some sets, then if those two sets are disjoint or not. That's what we want to know. So that was the multiphase problem, and Patrascu proved that if you prove lower bound for this problem, then it would yield lower bounds for several dynamic problems like dynamic reachability in graphs and so on. And you can also generalize this problem. And the query time is again the height, the depth of the tree, and you can generalize this problem for arbitrary function f. Okay, and so what's a semi-adaptiveness? Semi-adaptive data structure. As you could see, the update and query could be fully adaptive, and semi-adaptive data structure is such when we somehow mark the cells which were updated in the second phase, then during the query time, first we query the original cells, and after that we query the updated cells. But in this part of the decision tree and this part of the decision tree, the queries are fully updated, and the update phase is also fully adapted. So it's somehow restricted. And Koh and Weinstein prove that for this restriction, if the data structure is semi-adaptive, which solves the multiphase problem for disjointness, then it must have either big update time or a big query time. It means that basically during the update, it has to pre-compute all the results for all the queries, or all the computation should be done during the query. And so the holy grail is to prove such lower bound without the restriction of the semi-adaptiveness, but we are not so far yet. And our result is generalization of this theorem, and is that basically we prove the same lower bound for all functions of high corruption bound. So what is a corruption bound? So let's have some function from x times y to 0, 1, and we can somehow interpret this function as a matrix where rows are indexed by the set S, X, and the columns are indexed by set Y. And if we have some specific row X and column Y, then in the corresponding entry is the result of the function f on X and Y. And so we are talking about the rectangles. The rectangles is just a submatrix where one side is subset of X and the other side is subset of Y. And we denote the part of the rectangle where the entries are 0, the 0 entries bar by are 0, and the part of the rectangle where the entries are 1 by R1. And so given some distribution on the input, so x, y are distributed according to some distribution mu, we can define if the R is a row almost B monochromatic rectangle, if some inequality holds. What does it mean? That the most entries of the rectangles according to this distribution are B entries. So if rho goes to 0, it looks like this. So for example, if B is 1, then almost all the entries are 1s, and only small part of the rectangle are actually 0s. And now we can define what's corruption bound of the function parameterized by the distribution and the parameter rho. So the corruption bound is larger than S if there is some B that any rectangle which is almost B monochromatic has small mass. So for B equal 1 or 0, there are only small B monochromatic rectangles. So this is definition of corruption bound, and the corruption bound is used in communication complexity because it gives us a lower bound for communication complexity of the function. In the related terms with corruption bound is discrepancy, which is defined as this, that it's maximum over all rectangles, and between this of this formula, which says the difference between the 0 entries and 1 entries in the rectangle. And these two notions are related, because if the discrepancy is small, then the function has the monochromatic rectangles are small for the function F, but for both B. The main difference is between this quantifier, that for corruption bound, if it is large, then only for 1B the monochromatic rectangles are small. If discrepancy is small, then for both B equals 0 and 1, the monochromatic rectangles should be small. And the relation is that the corruption bound is bigger than logarithmic of 1 over the discrepancy. And if the function has small discrepancy, then it has large corruption bound. But the other way around, it does not hold, as disjointness has large discrepancy and also large corruption bound. It has large discrepancy because it has large, almost 1 monochromatic rectangles, but it has also large corruption bound because it has small 0 monochromatic rectangles. Okay, and so what's a balance distribution? So some distribution on X and Y is alpha balance if the probability that the function is 0 or 1 is at least alpha. So it says that the entries here in the matrices, there are the 0 matrices has some mass, and also the 1 entries have some mass. Okay, and now we are ready to state our result. So we said that the distribution over X times Y is a product distribution if there are two independent distributions, mu1 and mu2, such that mu equals mu1 times mu2. So now we state our result. So let's have some constant alpha and some product distribution mu, such that mu is alpha balanced according to a function f. So both 0 entries and 1 entries have some mass in that function matrix, and then we claim that any semi-adaptive scheme for the multiphase problem of F must have either large update or the query time is lower bounded by the corruption bound of the function F. So here this part is the same as in the theorem of Koh and Weinstein, and they prove it only for F being disjointness, and we replace the lower bound for query time by some complexity measure of F. And actually, we prove something more general. We prove it also for randomized data structures, for partial functions, and for smooth corruption bound, which is slightly more general notion than corruption bound. The proof is the same, but the statement of the theorem is a little bit more difficult. And so, what's applications of our theorem for some specific functions? So we can lower bound the query time of inner product by n. It's because inner product has a small discrepancy. We can bound the query time of disjointness to square root of n because the disjointness has a large corruption bound, and this is from our theorem. We by this application we get the same result as Koh and Weinstein got. Another application is for the function gap Hamming distance, which is the function, which is a promise problem. Alice and Bob gets the two string, which has either Hamming distance n½ plus square root of n, or at most n½ minus square root of n, and they need to decide if they get a close string or a far string in a Hamming distance sense. What's the proof idea of our theorem? So how Koh and Weinstein prove their theorem? So they define some random variables for the inputs of the multiphase problem, and if there is some efficient data structure for the multiphase problem, they derive from the data structure some random variable z and some I index to x1 to xk, such that the last bit of z is disjointness of xy y. Means the z has the answer for the function we are looking for. And the information what has z about x, y, and y is bounded by the query time of the data structure. So this I stands for mutual information. And also the information given z, which are between x, y, and y, is bounded by the update time over k, over the numbers of the strings xi's. So what does this condition means? If the update time is really small, smaller than k, then it says that xi and y are almost independent given z. And it says that z is similar to protocol of length tq times w, this thing. And the last thing what they prove is that such a random variable z does not exist for disjointness. So we replace this this last step, and we take this random variable z and prove that if some for function f, this random variable z exists, then the function f has B monochromatic rectangle of size 2 to minus TQ times W for both B. So it says that the corruption bound is upper bounded by this term, by query time times W. And that's all. And I am looking forward to discussion at the conference.